dan seluruh tamu-tamu kami. Sebelum kita mulai, maka kita mulai acara kita dengan lagu kebangsaan Indonesia Raya. Indonesia Anthem, please teman-teman bisa diputar. Okay, thank you very much for Indonesia Anthem. Dear honorable keynote speakers and dear distinguished and valuable participants, this afternoon, Karbon Research Center of University of Sumatera Utara presents a webinar entitled Atomic Force Microscope, Fundamental Solution and Applicants. So first, let us hear the report from our head of Karbon Research Center of University of Sumatera Utara, Ibu Dr. Nur Sahara Pasaribu. Time is yours.
Terima kasih Pak Dr. Bapak Rikson, PhD. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, selamat sore, salam sejahtera, dan good afternoon. Yang kami hormati Bapak Rektor Universitas Sumatera Utara, dalam hal ini diwakili oleh yang terhormat Ibu Wakil Rektor 3, Bapak Ibu Dekan di lingkungan USU, Bapak Ibu pimpinan Pusat Unggulan dan Pusat Kajian Lingkup Universitas Sumatera Utara, our honorable keynote speakers, Dr. Ivan Baikov, Regional Sales and Application Manager, NTMDT Spectrum Instrument Russia, Bapak Punidi SSI, Direktur PT Lab Sistematika Indonesia, alumni Fisika MIPA USU, dan seluruh tim PUI Karbon dan peserta webinar yang berbahagia. Bapak dan Ibu undangan yang sangat kami hormati, our honorable keynote speaker, this afternoon we are going to attend the webinar with entitled Atomic Force Microscope, Fundamental, Solution, and Application. This webinar is well organized and collaborated with PT Lab Sistematika Indonesia, NTMDT Spectrum Instruments, Russia, and Karbon Research Center, University of Sumatera Utara. We realize that our eyes, probably our mind that observe clearly materials, especially the nano-sized materials. In addition, reason, we need both developing direct evidence and simultaneous characterization. Those are physical, chemical, and electronic properties. Fortunately, Dr. Ivan Baikov would like be a speaker in our webinar today. He has more than 19 years experience in scanning probe microscopy, which is atomic force microscope, scanning tunneling microscope, and Raman, and etc. Hopefully, we might catch up many things from his presentations. Our distinguished and valuable attendance. Well, until now, I think our 2 years old already exists in our faculty since December 2nd, 2019. We realize our research center is quite young. We need to learn much more from the others and also gradually to improve our management, competencies, and networking. Finally, please welcome everybody and enjoy this webinar. Kami mohon dengan hormat kesediaan Ibu Arek 3, Wakil Rektor 3, untuk memberikan sambutan sekaligus membuka acara webinar kita pada hari ini. Demikian yang bisa kami sampaikan. Wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.
Yeah, thank you very much, Ibu Head of Karbon Research Center, University of Sumatera Utara. Next, we are going to remark speech from our Vice Rector, Ibu Popi. Silakan.
Assalamualaikum warahmatullahi wabarakatuh. Pertama-tama marilah kita panjatkan puji syukur kehadiran Allah Subhanahu wa taala yang telah melimpahkan berbagai kenikmatan kepada kita sekalian. Yang terhormat Bapak Rektor Universitas Sumatera Utara selaku penanggung jawab Pusat Unggulan Iptek Karbon, Ibu Dr. Nur Sahara Pasaribu selaku Ketua Pusat Unggulan Iptek Karbon, Bapak Rikson Siburian selaku Sekretaris Pusat Unggulan Iptek Karbon, Bapak Ponidi SSI selaku Direktur PT Lab Sistematika Indonesia, Dear Honorable Keynote Speaker Dr. Ivan Baikov, Regional Sales and Application Manager NT-MDT Spectrum Instrument, dan seluruh peserta webinar yang berkenan hadir pada hari ini. Sejak ditetapkan menjadi PTNBH, Universitas Sumatera Utara telah menetapkan rencana jangka panjang USU 2014-2039 yang dibagi atas 5 tahapan renstra 5 tahunan. USU telah menyelesaikan renstra 2015-2019, di mana desain ideal yang diharapkan bagi USU adalah menjadi universitas nasional terkemuka dengan akreditasi tertinggi dan merintis pengakuan internasional. Setelah menyelesaikan pengembangan tahap pertama pada tahun 2020, USU memasuki renstra 2020-2024. Pada tahap kedua ini, desain ideal yang ingin dicapai oleh USU adalah menjadi universitas berstandar internasional berciri keunggulan lokal. Berbagai kriteria terukur yang dijadikan tolak ukur keberhasilan universitas berstandar internasional adalah masuk dalam jajaran World Class University atau masuk dalam jajaran top 500 QS World University Rank. Salah satu upaya untuk mencapai target program kerja tersebut adalah mendirikan Pusat Unggulan Iptek. Kegiatan pengembangan Pusat Unggulan Iptek bertujuan untuk meningkatkan kapasitas dan kapabilitas sivitas akademika universitas, khususnya para dosen yang menekuni bidang riset tertentu dan khusus sumber daya riset dan jaringan iptek menjadi bertaraf internasional dalam bidang prioritas spesifik agar terjadi peningkatan relevansi dan produktivitas serta pendayagunaan iptek dalam sektor produksi untuk menumbuhkan perekonomian nasional dan berdampak pada peningkatan kesejahteraan masyarakat. PUI Karbon diharapkan dapat berperan sebagai lembaga litbang dan untuk mendukung dan mempercepat pencapaian program kerja USU tersebut. Melalui webinar ini, diharapkan kita mampu mewujudkan renstra USU 2021-2026 untuk masuk dalam jajaran World Class University atau masuk dalam jajaran top 500 QS World University Rank melalui riset ilmiah khususnya di bidang karbon. Berbicara tentang riset, maka diperlukan suatu instrumen sebagai pendukung untuk kegiatan penelitian dosen, dan menghasilkan publikasi ilmiah bereputasi internasional. Akhir kata, saya mengucapkan terima kasih kepada seluruh tim PUI Karbon dan PT Lab Sistematika Indonesia yang telah membantu terlaksananya kegiatan hari ini. Pimpinan universitas berharap kerjasama-kerjasama seperti ini dalam rangka untuk peningkatan kualitas akademik terus kita bangun dengan berbagai pihak. Dengan ucapan bismillah, saya buka kegiatan webinar kita siang hari ini. Demikian, wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Ibu Dr. Poppy. Yeah. Dear honorable keynote speaker and also all of participants, we will go to our webinar today. In front of us already join with us Dr. Ivan Baikov. He is a regional sales and application manager of NTMDT, and he gave us only short curriculum vitae. He succeeded to obtain PhD in nanotechnology, education physics, and math for applied science. And he has the outstanding experience, more than 19 years, in scanning through microscope. Yeah, this is a very many application. Like today, we will hear from him about atomic force microscope. Well, Dr. Ivan Baikov, time is yours.
Hello, everybody. I hope the connection is good, and I would like to thank all of you. So many people attend today, so I'm very proud that I will give the speech today for so many people, and I hope you will enjoy it. And if you will need to clarify anything, ask question or anything, please you can interrupt or write some question in chat or to Mr. Panidi or to me by mail, or just during the discussion we can discuss some key features also with you by asking some questions, and I will give a replies. So, and if you don't mind, I will start sharing my screen with PowerPoint presentation. Yes, and let's see how it goes. So I will just run it. Okay. So I hope you can see well the full screen of the PowerPoint, right?
Yes,
we got it.
Yes, that's good. And so today our discussion will be about atomic force microscopy, some principle of operation, some solution in the field of material science and biological application, medicine. So I will tell briefly which kind of measuring modes you can apply to analyze your samples and so on. And so main application which are famous nowadays with the help of the atomic force microscopy and also combined techniques, because for example nowadays the big jump forward is to combine the microscope with the other techniques like QSM, STHM, Raman, TERS, IR systems, so you can get some complex information from one measurement in the same time, and you don't need to move the sample from one instrument to another. So let's go forward. So briefly, a few words about our company. So our company exists more than 30 years, and the headquarters is located in Russia. And we have the few offices worldwide in the China, US, and Europe, many distributors worldwide. And nowadays we are proud to say that we have instruments in a few thousands of different places worldwide. So it can be some instruments for the beginners, and could be some flexible and very advanced systems for very high research in the cyclotrons and some factories and so on. So, and shortly about the main products in our line. And so we have a few instruments to cover different applications and the different tasks of the customer. So for example, the first one on the left, you can see is called like Solver Nano. This is a quite basic AFM with the option of using for education, because it has some specific special measuring head which use not the standard cantilever accessories for the measuring, but the special wire that you can do by yourself. So you don't need to spend like a budget to buy the new accessories. So you can do them by yourself. So this is Solver Nano, quite basic system, but in the same time with the cantilevers, you can do the normal scientific research for main field of the AFM application. So it has like atomic force, scanning probe, it has a temperature control, it has a option of operations in the liquid cell for biologic study, and so on. So the next one is called like Next or Titanium. So the main feature of this instrument that it can work with it's good for automatic measurements, automated. So because this unit has many motors inside, so all the manual operation in this machine is motorized, means from the software. So you can put your sample by hand and then just operate by the software. I mean, you can adjust the laser and photodiode, you can move the sample, you can move the optics up and down, left, right, you can make focus and zoom, you can change by the software the two heads, AFM and STM, between each other. So all the other operation is done automatically. So this is the idea of this machine. The main instruments we have, the most flexible and modular, is called Integra. It has a great number of different options, configurations, modifications that can cover any kind of the application area, from material science to biology and any other. It has, for example, up to 10 types of different liquid cell for small volume, big volume, with flow through possibility, with heating or cooling, and so on, with a petri dish operation. And the same, it has a great number of options for material science, like it can operate in the low vacuum, it can do the electrochemistry, it can operate with external magnet, with a microtome, with scanning thermal microscopy, with Raman tears, and so on. So this is like this product. And the next one is called Vega. So Vega is a big machine for the industrial application because it has a big stage for the samples up to 200 millimeters wafers, and you can do also the automatic research and quality control or roughness measurements or any other measuring modes is supported here. So it can also operate in the fully automatic mode with the full control of laser, photodiode, optics, sample. So you can make in advance some scenario of the measurements of the big wafers in the many number of points, then run the measurements, and the system automatically will move from one point to another, collect some images, do some calculation of the roughness or other parameters like hardness or Young modulus, and then give you report for different points, make some statistical analysis, and so on. And the most complex system is when you combine the AFM with the other analytical methods. And one of the instruments is called Integra Spectra. This is the instruments when we combine the Integra AFM with the Raman and TERS. And so in that case, we have the AFM and next to it Raman. So from the some laser sources, CCD cameras, and so on. So in that case, we can make simultaneous measurements of the all the AFM techniques, I mean topography and other properties, plus optical techniques from the same area in the same time from one software. So it's very easy, professional, and you don't need to spend time to correlate the images after and to get some extra information or to move the sample to another instruments, find the same area and so on. So in that case, you get the same image, the same area in the same time. So you can easily understand what is the correlation between topography and some nanomechanical properties or electrical properties and some optical properties from confocal Raman, fluorescence, and so on. And the other technique the other instrument is called Integra IR. This is when you combine the Integra machine with scattering snow techniques. So this is the difference between spectra and nano IR is the source, because in Integra spectra we use mostly visible and near infrared sources. In Integra IR we use infrared sources, a few microns wavelengths lasers, and measure the scattering snow techniques. So this is a full range from the very basic AFM to flexible AFM, automated AFM, to some complex study with other analytical method combinations. So, and now briefly, we will discuss about the principle of operation of the AFM atomic force microscopy. So I hope you hear me well and the screen is still visible, right?
Yes, Dr.
Yeah.
Yep.
Okay, that's very great. So, so few words about the principle of operation. So in atomic force microscopy, or in general scanning probe microscopy, there are three different principles. Depends on the probe that we are using. So the most convenient, the most conventional one is atomic force, and in that case we use a silicon chip with a small lever and the tip at the end that you can see in the center. And we use the optical registration system, which is some laser and photodiode. So the laser comes to the cantilever and the reflected beam goes to the photodiode. So from the photodiode, we measure the displacement of the laser spot, which is proportional to the deflection of the cantilever, which reflect as some topography and properties of the sample. So in case of scanning tunnel microscopy, on the left, we need to use some conductive surface sample and the special wire. So instead of silicon chip, we use just a wire, which is usually like conductive wire, maybe tungsten or platinum iridium, and so on. And as feedback input signal, we use the tunnel current, which is coming between tip and sample. So by controlling the value of this current, we can control the conductivity, the surface, and so on. So the great limitation here is that the sample should be conductive. So if sample is not conductive, we cannot apply the scanning tunnel microscopy. But the big advantage of this approach is that in comparison with the cantilever, which has a curvative radius of maybe 5 to 10 nanometers, here in scanning tunnel microscopy, we can prepare the probe by cutting the wire or by etching with a curvative radius of atomic resolution at the end. So I mean below 1 nanometer. In that case, the resolution of these techniques can be much higher. And the third one, probe that can be used in scanning probe microscopy is a tuning fork on the right. And this approach is used for optical application, which is like a scanning near field microscopy, SNOM, to measure the optical properties. Here we can measure the transmission properties or reflection properties or fluorescence properties of the material. And in that case, we have some kind of tuning fork and we attach some fiber to the one side of the tuning fork. And we control the distance between tip and sample by oscillation of the tuning fork. and in the same time we introduce some laser radiation inside of the optical fiber. So in that case, we work at the very close distance to the sample, and we have some optical signal coming from the fiber, and we can analyze the reflected or transmitted signal from the surface or through the surface in case the sample is transparent. Yes, so go further. Okay. Okay, for here. So here, how now we switch more to the atomic force microscopy principle, and here you can see the basic scheme how the general atomic force works. So you can see in the center we have the sample, which is blue. Under the sample, for example, we have the scanner, which move our sample left, right, and up, down. So from the top of sample, we have the cantilever, which can deflect the lever, depends on the force interaction between tip and sample. Then you can see the laser from the right, which comes to the cantilever, reflected beam goes to the photodiode, like you can see AB, and from the displacement of the laser spot on the photodiode, we can understand what is going between our tip and sample. And so depends on what we need to measure, topography or some properties, we can arrange different type of the feedback loops, how to measure topography, relief, and so on, or some electric properties, magnetic, lateral, friction properties, and so on. And on the right, you can see some small animation, how the sample and tip interacting and going. So for example, you can see how the scanner follows the sample. So we can measure the vertical tip position, and our feedback loop keep the deflection of the cantilever constant by moving the scanner up and down. And this movement of the scanner up and down, we consider and interpret it as topography in our case. And as results, we can obtain such image, which you can see in the center below, that, for example, some image of some structure, which you can see in the 3D. Okay, go to the next slide. So, and here some description of the limitation of the general scanning probe sensor. So the sensor is a tip, cantilever, and depends on the curvative radius. Like, for example, in that case, it's like 10 nanometers on the image. You can understand how will be our structure, depends on the tip shape. For example, if we have the structure of 1 nanometer, and since our tip has a radius like 10 nanometer, we always get the AFM profile like you can see on the top right. So it will be not like a round structure like DNA or nanotube, for example, but you will see something like on the profile, which is limited by the probe shape. But nevertheless, with a regular AFM in the spatial techniques, we can get very high resolution. For example, this is the atomic resolution on graphite, which is high-oriented pyrolytic graphite. You can see here the two images in blue. This is this size of the images is just a few nanometers. So on the left, you have roughly 10 nanometers. In the center, you have just a few nanometers, like 2-3 nanometer size images. And for the biologic resolution on biologic samples, you can see on the right some proteins and molecular resolution with the size of the scanning, which is like 300 nanometers only. So you can see the few particles on the surface. Their size is just like 10 nanometers only. So this is a kind of the critical resolution we can get with the atomic force microscopes. So, and if we compare the atomic force microscope with the other analytical method like optical microscopy or electron beam microscopy or transmission electron microscopy, then the big advantages that resolution we can get here in the XY range is down to 1 angstrom in XY, and also below 1 angstrom in Z direction. And in atomic force, we don't go inside of the sample, but we measure the surface and some properties, which is very few nanometers below the surface. And the good point that you don't need specially preparation of the sample. So you can just cut some material, make some preliminary polishing, and measure it. Okay, go to the next one. So just to conclude some highlights and advantages of the atomic force application, which is like high resolution. That the second one is that always you measure not only XY contrast, but also the Z dimensions. So the full 3D image for the topography in X, Y, Z in nanometers you can obtain always. The next one is that with AFM you can measure the samples not only in air, but also in the liquid environmental, in vacuum down to high vacuum and ultra high vacuum, and some specific media like some aggressive media for electrochemistry and so on. The next one is that always you can do the complex study. So you will measure not only topography, relief, but in the same time from the same area with the basic AFM, you measure different physical, electrical, friction, and optical properties. So this is a very good advantage. The other one is that you can use the atomic force microscope not only for analysis, but also to do some treatment of the sample. So since you have the full control of the cantilever and the sample, and you can move it any way you want, and also you can apply some positive or negative voltage between tip and sample. So in that case, you can do some modification, and modification can be mechanical when you apply some force to the soft issues, or it can be electrical modification when you apply the different voltage between tip and sample, and you can change the distribution of the electric properties, or you can also grow some oxide layer on the surface of semiconductor. And also by introducing some optical interaction, putting some laser, you can also excite some reaction on the photosensitive materials. Yeah, and one of the other interesting application is a single molecule study. This is done when you put some biologic molecule on at the very end of the tip, and then this tip can go to interaction with some biologic molecule on the sample surface. In that case, you will study just a single molecule force between the molecule on the tip and other molecule on the sample. So that is very precise and accurate measurements, but you will get the very interesting results. And the last one I would like to mention here is the possibility to combine the atomic force with the other analytical method, as I mentioned before, so which is Raman, tip-enhanced Raman spectroscopy, thermal microscopy, QSM to measure the changes of mass at the nanogram level. Yeah. So now let's, okay, then I run this one. There is some animation here. One more. All of this. Okay, you can see some few animation which show you different techniques, principle of operation. And in general, there are more than 40 different measuring techniques available nowadays with basic AFM, which allow you to measure the topography at the different with the different measuring modes. It can be soft interaction, hard interaction, or any other. You can choose, depends on your tip, depends on your sample, and depends on the and depends on the properties of your objects which you want to study. So go to the next one. So here is some list of the very main techniques that are used by our customers and by us to do the analysis of the sample. So as you can see from the scheme, you can apply the AFM to different research areas, from medicine, sciences, biology, chemistry, engineering, material science, physics, metrology, and any other. And all these techniques in the list on the left provide us different information about the surface at the nanometer level. Nanometer, I mean, so if you measure, for example, the friction properties, since we have the probe with the nanometer size radius, we will measure these friction properties also at the nanometer scale. The same with the surface potential, the electrostatic forces, capacitance properties, conductive properties, magnetic properties, and so on. All these properties can be measured at this very small level, and you will get a very high resolution. Yeah, this is about this techniques. There's some advanced techniques which are used for analysis, which is like for conductivity measurements, we call it like spreading resistance. And for magnetic field, we use like MFM technique, Kelvin probe to measure the work function and surface potential, and the piezo response technique we use to measure the piezo effect. And here is a slide which represents you one of the example how we can use the AFM to modify the surface. So for example, here you can see the image of the carbon nanotubes on the silicon substrate. The size is below 3 microns, and on the left you can see the image of the carbon nanotubes obtained without any deformation or strong interaction between tip and the surface. And then we use the tip as nanomanipulator, and we move it left to right, and we turn the nanotube on the surface by applying a bit more higher force. And then we scan the same area with low force interaction again. And you can see the results on the right image. You can see after the tip, we move from left to right. You can see that how the shape of the nanotube is changed. So in such way, you can do all kind of the nano manipulation with the surface at this nanometer scale level. So another example of the modification that you can do with the atomic force probe is the charging of the surface and local oxidation lithography. So if we have some thin film of some semiconductor material that you can see schematically on the left, then we can just apply some voltage between tip and sample by the AFM, and depends on the voltage and depends on the duration of the staying of the tip at the single point. We can grow the different size of the oxide layer on the surface. So you can see on the bottom the two-dimensional image of the results depends on the how long we stay at which point. You can see that we have the different size of the oxide layer on the surface. And also on the right, you can see the 3D image of the same area. And you can see how it looks like. We have the height of these lines of about few nanometers, from 1 nanometer to 4 nanometers. And the 4 nanometers is the right line when we apply the voltage at the much longer time. So you can see and how we modify the surface, and it's not a charging of the surface. So it's really, we grow the oxide layer on the surface, which remain forever on this surface. So in such way, you can do some modification and maybe create some nano objects on the structure of the thin films. Yeah, and here the next slide represent you how the general operation in the software is done, and we try to do it as much as easier for the customer, so you don't need to spend more time to adjust many parameters and tune the techniques. So here, for example, in our software, you need to first one to find the optical image of the cantilever beam of the photodiode, so the aiming, how the reflected beam looks like on the photodiode. Then you switch to choosing of the type of the approach. It can be done in contact mode or in semi-contact mode. So in contact mode, we just use the static deflection of the cantilever. In semi-contact mode, we drive the cantilever at its resonance frequency, and then we keep this a magnitude of oscillation constant at some level for the feedback loop operation. So if we need to operate in semi-contact, we just click search for the resonance frequency, and the software automatically finds us this resonance frequency. Then we switch to approach window and click button approach and or landing, and the software automatically approach the tip to our sample. Then we switch to scanning mode, and here we need just to choose the technique which we want to measure. It can be like just a topography or some properties like friction, electrostatic, magnetic properties, and the software automatically will do the required configuration of the electronics, and you just click run by choosing, and also you need to choose some size of the area that you want to study. Click run, and you get the image like you can see on the right. Yeah, in the same time, in our software, we have the very powerful image analysis module. So you don't need to export the images to some extra software to do some analysis, treatment, or statistical measurements. But still, there is an export menu, and you can export all the data to any software you want. But if you like, in our software, you can do all necessary treatment and analysis, what you can do. For example, here you can see the screen of the image analysis software with a few data on the left, with the actual data in the center, and on the right you can see the many number of different filters, corrections, transformation, editing, and there are like up to 50 different filters that you can apply to the images for editing. Also, for example, in case you have some sample with some particles distributed on the surface, the software automatically can calculate them, and not only the numbers, but also some statistical parameters for each particles that you can see on these images. So on the left, you have the image of the scan structure. On the right, you can see how the software calculate these particles. And for each of the particles, it makes some table with a number of particles with some statistical parameter or average size and so on that you can put in some of your reports. Okay. And now we speak more about some material science applications. Okay, here is a window. I will run it. So one of the interesting techniques is called spreading resistance, and it's used to study the conductive properties of the sample. So the idea of this technique is that we use a conductive probe, we use a conductive sample, and we ground the sample and apply some voltage to the tip. And depends on the conductivity on the surface, we can measure the current. We can measure the current at single point or at some grid, or we can do the scanning, XY mapping, and at the same point, at the every point, we will measure the current. So finally, we will get the distribution of the current with a constant voltage applied between tip and sample. So as a result, we can see such images, for example, as you can see on the slide. So this is like a film, titanium silicon grains on the conductive phase. So on the left, you can see just a topography with the dimensions of below 200 nanometers. And on the right, you can see the current distribution of the same area during the same measurements. And the voltage which was applied between tip and sample is just 20 millivolts. So you can see that the two images do not correlate to each other. So it means that from the topography, we cannot distinguish what are these areas, are they conductive or not. But from the current images, you can see clearly, okay, so these islands are more conductive because we got the current of this area at this level with the constant voltage. So this is a very good technique for material science to measure the conductivity. So here is the other examples, which you can see here. And the sample here is a titanium oxide film on the silicon substrate. And you can see on the left, again, there is a topography with a scan size of about 900 nanometers. And on the top area, you can see some particles, which are most likely having some dielectric properties. So it's not conductive. Therefore, on the right images for the same area, we get this scan. And you can see that at this area where we have the particles, there is no conductivity at all. So we apply the voltage, we try to increase it, but still no conductivity, which help us to understand that, okay, these particles is not conductive, so it's not titanium oxide, and maybe it can go to some further analysis of the sample. So here I would like to draw your attention that the resolution of such measurements, the topography, but also the spreading resistance, the conductive measurements are very high. So you can see here the particles and the image on the previous slide, which has a resolution of the few nanometers only. So here there is example. Here you can see the example of the voltage lithography, and again there is a semiconductor film, and you can see that on the topography image, which you can see on the bottom left, there is nothing visible. But if you apply the different measuring modes, one is the current, for example, on the right bottom, you can see some current contrast, which show us some differences down to only 30 femtoamperes resolution. So it's a very low resolution for the current. And also, if we apply the other measuring modes, which is called like a lateral force, which show us some information about the friction. And you can see on the top images that the friction in different direction is different on these squares where we applied the different voltage by lithography operation before. So this slide show you the high resolution for the current measurements. So it's not like nano or microamperes. So it's down to a few tenths of the femtoamperes. So here you can see an example of the other measuring modes to measure the magnetic properties. It's called like MFM microscopy, magnetic force, and you can see how it works. The first, we scan the sample, we scan the topography during first pass. Then we return and scan the same line at some distance from the sample and measure some phase shift or magnitude of oscillation, but following the topography at some distance. And since we have the cantilever, which is coated by magnetic coating, then this magnetic coating can feel the magnetic distribution of the sample, and we can measure the magnetic properties on the surface. So why we cannot to measure the magnetic properties in the same time with the topography? Because the repulsion force, adhesion force, and van der Waals force will be much stronger than magnetic forces. But going far away from the sample at the distance maybe 100 or 200 nanometers, there will be no such forces, and only long-range forces will act between tip and sample. So in that way, we during second pass, we can measure the magnetic properties. And such technique like magnetic force microscopy is always operate in the two pass, just to avoid the influence of the like topography forces, let's say. As a result, you can get such images on the hard disk. So the hard disk from the PC, like data memory, so you can see the different example with the different resolution and the different hard disks. For example, on the top, you can see like a low data density image. The size is like 33 microns, and you can see the magnetic domains, like they're responsible to 1 and 0, 1, 0, 0, 1 information. So the sample with medium data, you can see that the same size, 33 microns, but domains are much smaller. So it means that capacity of this hard disk is much higher. And on the images below, you can see the size on the left is only 3 by 3 microns, but the domains, magnetic domains, are not parallel to the surface, but they're vertical. And in that case, you can put much more information on the same area. So that's why this is a scenario for the high density, high capacity hard disk. Okay. Also, atomic force microscopy allow us to measure some properties depending on the temperature and the heating control. So here we have the different type of the heating stages, which can heat our sample or cool our sample also at the different level of the temperature. And you can see on the right, the same topography of the polymer can change, depends on the, no, so it's not the polymer, so this is a magnetic force images on the cobalt monocrystal, which depends on the temperature of the sample. So you can see how the magnetic properties are changing, depends on the temperature from 200 degrees to 300 degrees. So you can see that the structure is totally reduced under very high temperature. Also, for example, Integra atomic force microscope allow us to operate in the vacuum condition. So in principle, it can operate down to 10⁻⁴ torr. And this allow us to avoid any kind of contamination or water inside of the measuring space, to avoid some parasitic effects. Also, many magnetic sample does not have does not show any magnetic properties with the under the ambient conditions. In that case, they will require to apply some external magnetic field for them to show some magnetic properties. And in our case, we have both possibility to apply the in-plane external magnetic field and apply out-of-plane external magnetic field. In both cases, you can control the value of the magnetic field from the AFM software. So you choose the different value of the magnetic field and measure the magnetic properties together with topography. Then you can change it and measure again, and then you can compare the two images to understand at which value of the magnetic field the magnetic properties are changing or appear in some structures. And here is some example of the different sample which show you differences in magnetic field. So yttrium iron garnet film, for example, on the bottom, or cobalt monocrystals on the top. So on the top, for example, from the left, you can see the topography, and on the right, you can see the same area obtained in the same time, but which show us the magnetic field distribution, similar to the images on the bottom. And here is an example which show you the changing of the magnetic field and the different magnetic field, external magnetic field. So we increased the magnetic field from 0 to 1500 Ersted, and you can see how the structure is changing also. And the sample is some domain structure of some sandwich structure. So it's a gold together with the cobalt. So now we switch to some example of the electric properties study. So briefly, just to have you idea, to give you idea about its operation. So again, we use the two-pass technique, for example. First, we measure the topography, then we return to the original point. At some distance, we apply DC voltage and AC voltage. And according to special algorithm, we can measure the work function or surface potential of the particular area on the surface. Also, alternative way is to use the single pass Kelvin probe microscopy when we apply the driving voltage for the mechanical oscillation and driving voltage for electric oscillation at a different frequency. In that case, we can measure topography and the electric properties in the same time without two passes. So here you can see some example of the images of surface potential. So it's nanotubes distribution, and you can see on the left the topography, and on the right this is a surface potential of the same area. And you can see the different size nanotubes show different surface potential distribution on the right with quite high resolution. So the scan size here is about 6 microns in XY. Well, here you can see the image of the lithography operation. So there was some lithography was done before on this particular area on the gallium arsenide substrate. So we applied like positive and negative voltage on the same on this area, on the white and black one, and then we scan the results in the Kelvin probe microscopy, and you can see on the topography appeared nothing, but on the surface potential images of the same area, we see how the surface potential is changed at this area. So on the white area, we apply one side of the voltage, one sign voltage. On the other black, more dark area, we applied, let's say, negative voltage. So this is example how like we can use it for modification of the surface. And here is the example of the Kelvin probe microscopy, which is Kelvin SKM for fluoroalkane on the silicon. So here the you need to pay attention that the scan size is only 1 micron, and you can see very high resolution for topography and for surface potential. So on the left is the topography, height, and surface potential on the right. Here I will run also this animation. So another interesting measuring mode is called like piezo response force microscopy, PFM, and it allows us to measure the piezo effect properties on the piezoelectric material. So from the animation, you can see how you can. So this technique is operated in contact mode. So we stay in contact with the surface, and then we apply different alternative voltage between tip and sample, and the tip should be conductive. And depends on the piezoelectric properties on the surface, we will have the different response on the cantilever. And by measuring this response, we can understand if it's higher or lower, or if it's left, right, or up, down. We can understand what are the domains, piezoelectric domains on the surface. Well, and here is some results. So on the top, you can see just a mapping or imaging, the topography of some piezoelectric film, and the piezoelectric properties on the right. So you can see that they do not correlate to each other at all. So it means that it's definitely piezo response effect. And also, if you have some domain structure, by applying the different voltage, different constant voltage to between tip and sample, you can switch the piezoelectric domains. And this is called like a domain lithography. So you can see on the bottom two images that you can actually draw some pattern on the surface by switching the piezoelectric domains on the surface, and they will remain forever until you do not switch with the opposite voltage again. Okay, and here you have some example of the polymer study and organic film, just to understand that it's also that AFM is also applicable to soft material and not only to hard material, some semiconductor film. So you can see here some images of different type of the polypropylene, polyethylene oxide, spherulite sample, and some copolymer with different size of the scan, from 15 micron down to 1 micron and 5 micron. You can see different structure, and the sample is much softer. So in that case, we need to apply some more gentle techniques, which is not contact measurement, but semi-contact, tapping mode, or non-contact operation, when the interaction force is very, very low. So it's just to avoid any kind of interaction and deformation on the surface by the tip. Well, this is a example of the study of the also some semiconductor film, self-assembled film, and on the left you can see the topography, and on the right you can see the electrostatic field. So there is one technique which is called AFM, so electrostatic force microscopy, which works similar to magnetic force microscopy, but instead of magnetic probe, we use the conductive probe. So, and finally, our conductive probe can feel some electrostatic charge on the surface. And here you can see the results. It's again the topography and the electrostatic field, and they do not correlate each other on the same area. Well, here you can see again some example of the nanolithography and nanomanipulation. So even you can make some drawing on the surface of the film. So if you have some pattern in the graphic format, you can load it to our software, and then by applying the different voltage, you can change the charge distribution, or you can grow, like for example, channel with a width of a few nanometers only, that you can see on the top right. So here is another example of some nanomanipulation and nano machining and so on. Now let's switch from material science to some biologic and soft issue application in liquid and on the soft samples. So which kind of materials can be studied for the biology? So it can be some big objects like cells or tissues, and here you can see example of the human leukocyte. Then it can be some viruses, and you can see some Ebola virus with few micron size, or you can go down to some molecular level and measure some very small features like immunoglobulin antibody molecules with the size of just 10 nanometers. You can see on the bottom. Yeah, and if you just to know you about the setup which is used for biological application, of course, most of the objects for biology need to study in the liquid, in the special solution, just to keep them live. So in that case, we have the different type of the liquid cell, or you can measure with the Petri dish. So somehow you need to fix your object on the bottom of the liquid cell or Petri dish, and then with a special tip holder for liquid, you can go inside to this liquid cell and measure the topography and the properties. Okay, again, I run some animation. Okay, and the most problem here with the soft sample and operational liquid, especially, that very strong interaction, of course, will disturb our images, and the objects will be destroyed or modified, like you can see on the image. So after scanning with a high interaction force, the image is not nice anymore, and we cannot get clear image. So just to solve this, we use this resonance technique in the liquid for the biologic application, which allow us to reduce the interaction force many times. Okay, and one of the application, one of the solution for the measuring biological objects is use the special like a hybrid mode technique, which do the movement between XY points on the area out of the contact with the surface. So in every point, the tip do approach to the surface, measure the topography and other properties, then it do the retraction and move to the next point. In that way, we can avoid any kind of the lateral pressure on our objects. So this allows us to measure the clear structure and boundaries of any kind of very soft biological object without interaction with them, and without especially the lateral pressure on it during the scanning. So here is some example of high resolution of the streptavidin biomolecules. In that case, we use the special DLC tip, which is like some kind of carbon nanotube at the end of the cantilever with the higher aspect ratio and curative radius. And you can see the high resolution, which show us like just a few nanometers of the resolution on the streptavidin molecules. And here there's example of the measuring of the single collagen molecules from the rabbit skin. And you can see the topography on the left, and also by making the section of one molecule, you can see that the size, the height of the molecule is just a 5 angstrom. So it's okay. Here also atomic force microscopy, since it has full control on the tip sample interaction, you can measure also the mechanical properties of the objects. And here is example of the elasticity measurements on the cell, on the kidney epithelial cell, on its fragment. And you can see we measure the scanning of the mapping of some area, and then we compare the Young modulus in the different area, like 0.1, 2, and 3. 0.1 is just a substrate, and 0.2 and 3 is the different thickness of this cell, and calculated the Young modulus, and you can see the three numbers of it. Here is some other example of the biological objects that can be studied in AFM. So it's linear DNA molecules on mica obtained in the solution. So you can see these DNA molecules. This in the center you have some membrane protein nets with the size of the image of 1 micron only, and the big bacteria. Another examples is another cells. Then in the center top you can see the image of the human hair. So it just some shells on the human hair that you can easily resolve it with the AFM. And then some another molecules, ribosome activated toxin on mica in air, and some implantant used for arterial matrix. So if you compare the two images that we measure in air and in the solution, in the buffer solution, that you can see how the single peptides can be visible on the. So on the left you can see measurements in air, and on the right in the liquid, in the like native solution, native condition. So another examples of the different cells. So for example, on the bottom left, you can see the same scan of the lymphoma cancer cell, which are like distorted cell, and other cells. And in the beginning, I mentioned about one interesting application to study the single molecule interaction. And here, some principle how it works. So we use the AFM probes, we use some linker and attach some biotin molecules to the end of the tip, just a single molecules. And then if we have some surface and some distribution of the other molecules, then from the animation on the left, you can see how we can study this interaction. So we approach the different area and see this interaction, and depends on the deflection curve, we have the different shape of the curve. In one case is a big interaction, in another case is smaller. And since we know that the cantilever is modified by this single molecule of biotin, we can understand even the force of interaction. So now let's switch to the next slide. So here is some other explanation of calculation of this binding force, how it's done. And okay, and the next one. Yeah, you can see how these biotin molecules interact with the streptavidin molecules on the surface. By the way, on the left, you can see the topography. And you can see that the surface is full covered with the streptavidin molecules on mica. And but these streptavidin molecules can be located in the different way. So one can stay like vertical, another is tilted, and so on. So this will show us a different binding force, of course. So by doing this approach and retraction in different point, we can measure this curve on the left bottom and then make some statistical data analysis. And from this statistical data analysis, we can calculate exactly that this binding force is, since we know the stiffness of the cantilever, which is deflecting during these measurements, we can calculate the binding force. And from this statistical calculation, it appeared to be about 44 piconewtons, which is accordingly fit to the theoretical data between interaction of these two molecules. Yeah, so this was about the single molecule interaction application. Now, a few slides about how we can integrate the basic AFM with the other analytical methods and which information it can provide to us extra. So, and here I would like to explain, there are many of them combinations, but the most recent one and most famous is like integration with the quartz crystal microbalances, then scanning thermal microscopy and Raman confocal microscopy. So for the first one, so the integration means here that inside of the liquid cell or gas cell, we put some quartz resonator, which can shake our sample or our powder or layer at its resonance frequency. And then we can put inside of the liquid cell the different media, like liquid or gas and so on, and some particle can be attached to the surface of the sample. And then by measuring of the frequency shift, we can calculate the changes of the mass of your sample. And the good point is that we can go to some nanogram level by measuring these changes of mass from the frequency, or from the shift of the frequency of the resonator. So for some application, that is very valuable and possible to do with the AFM. Another application is good for some material on polymer study, when you need to study some thermal properties, but to measure not under different temperature, but to measure directly the thermal conductivity, or to do some modification of the sample by a heated probe. And here is example of the measuring the thermal conductivity. So that is on the left, some optical fiber inside of some epoxy glue. So the distribution of the thermal conductivity on the left, and on the right, you can see the topography of some polymer after we put the tip at the particular point and increase the temperature of the tip above 67 degrees, which is the melting temperature of this sample. And then we do some melting of it. This is a bigger scan size to show you this spot on the sample. For very complex operation, we can use such a breakout box, which is fully compatible with any kind of the products. So you can see that this box you can put between AFM unit and its controller. So it means that all these connectors allow us to interrupt any operation of the AFM forward and backward. So we can do our own scanning, or we can put some external signals, or we can measure some signals from the controller and analyze them with some external device. So any kind of customized application are possible to do in that case. Yeah. Yes, and one of the most powerful combination is the combination of the AFM with the Raman. So next to AFM, we put the Raman spectrometer with up to 5 different laser wavelengths, with a detector, with a pinhole, and we arrange the confocal scheme, which allow us to use to measure the confocal Raman, fluorescence, tip-enhanced Raman, and fluorescence microscopy near field, and reflected laser confocal imaging. And here is some example of for example, in the center top, you can see just the optical image that you can see with the optical microscope. And the sample here is graphene. And on the right, you can see the topography of the graphene flakes. So it's the scan size of about 50 microns. And you can see few flakes on the top. So then from the same area, you can collect the Raman signal from the 2D peak, which is responsible to the number of the layers of the graphene. And you can see on the left that a color represent as the Raman signal, and the higher signal means bigger number of the flakes on the in this area. So you can see these combined measurements in the same time. When you measure topography and some Raman signal, you can understand better about your structure. And here is example of the complex study of the same area using AFM and Raman. So on the left top, you can see lateral force, which show us some friction properties on the graphene, then electrostatic force distribution, then force modulation. It is about mechanical properties, about elastic properties. Then it's a work function of the graphene flakes. Then it's a topography. Then it's a Raman map, mass center of 2D band shift. Then it's a relay microscopy and Raman map G-band intensity. So you can see that all these measurements can be done. Again, I would like to put your attention from the same area in the same time. And here is example of some application to measure the tablet, which contain of the two components. One is a paracetamol and another is aspirin. So when you measure the topography, AFM height and AFM phase shift, you can see almost nothing on the image, and you cannot understand which components corresponds to which area. But when you measure the Raman shift, then you can see clearly which area corresponds to which material, because you have a database of all the material and Raman peak shift, and you can understand, okay, well, this area in the center corresponds to paracetamol. The other green is the aspirin. And as you know that there are some limitation, which is limited by diffraction for the optical study, which is like half of the laser wavelengths. So it means that by introducing some laser at the like some green light, for example, with the 500 nanometers, we can get some resolution of 250 only nanometer for the optical study. But by combination of the AFM with the Raman confocal microscope, we can dramatically increase this resolution. And this is possible because of the TERS. It is a tip-enhanced Raman spectroscopy. So for this, we need to use the special probe, which is coated by gold or silver, and we need to put the light with the correct polarization on the tip. And finally, due to the plasmon resonance, we will get the dramatical increase of the intensity of the Raman signal, which is located only at the area under the tip. And since our tip is not few hundred of nanometer, but few tenths of nanometer, then by this technique, we can increase the optical resolution from few hundred nanometer down to few tenths of nanometer. So down to 10 or 20 nanometers only, which is for optical resolution. And here is example of the study of the carbon nanotube by this TERS effect. On the left, you can see the two spectra image. Black one is when the tip is retracted from the surface, and the red one is when we approach the tip to the surface and appears this plasmon resonance effect. So the signal is dramatically increased just on the area under the tip. So finally, you can see the Raman map of the carbon nanotube on the right, which show us resolution of about 250 nanometers. And this is the same size, the same scan size, which show us resolution of about 50 nanometers only on the carbon nanotube, just because we put the special probe with correct polarization of the excited light, when we got this resonance effect under the tip, so we collect the signal only from the tip, from the area under the tip. So this way, we can increase the optical resolution by combination of AFM with the optical Raman study. And this is the topography, for example. Yeah, and just to remind you a bit about the just the main products that is possible to put in the lab to use for research and so on. So the basic one, which is good for basic research and also for the education of the new people, is a solver nano or nano educator, which has like a AFM and STM special head for the piezo probe operation, with which you can build by yourself. At the same time, you can use also the regular commercial cantilevers here. So the other one is a machine like a solver next or titanium, which is like fully automated machine for AFM, STM, and it has like full materialization inside. So you just need to put the sample and then do all the operation by the software. I mean the mechanical operation. So the most important that you don't need here to even to adjust the laser and photodiode to put the laser on the tip and catch the reflected beam. So from software, we'll do it in a few seconds for you. And this is an Integra. This is Integra, which the most flexible and modular system with lots of option and possibility to integrate and combine with the other methods, like with the Raman, with inverted microscope, and so on, for complex research. And this is a good point for some scientific center, because you can have one controller, one basement, but different type of the heads, cells, and some accessories that can be used by a different group, by different people for different applications. So they come to take the measurements. One head can be, for example, dedicated for polymer study. Then another group can use the Integra for magnetic study operation, since it has a magnetic external magnet. Another another group can work with the STM, or another for optical study, but still the controller, the software, the basement of Integra can be just a single one for all these people. Yes, and the most powerful is this Integra Spectra, when we have this Integra in upright or in inverted configuration, combined with the Raman, TERS, and SNOM. So here I would like to thank all of you for your attention, that you listen me, and if you have any questions, raise them now, or you can write to to my colleagues in Indonesia, or to me by mail. So it's up to you. Thank you very much.
Yeah, so, thank you very much, Dr. Ivan. Very interesting presentation. Yeah, I am very surprised that the AFM may apply to many applications. Yeah, this is very surprise for me. Yeah, previously I used a scanning tunneling microscope combined with scanning tunneling spectroscopy, STS. So this is only for graphite. We apply for surface of graphite, right? But I am very surprised based on your presentation. We may apply many application and measurement based on one apparatus that's called atomic force microscope. Okay, well, dear participants, if you have some comments or some question to Dr. Ivan, time is yours. Okay, I open the question and answer. Silakan Bapak Ibu. Sorry, Dr. Ivan, I changed to Indonesia bahasa.
Yeah, it's okay. It's okay. Sure. No problem.
Okay. Bapak Ibu,
okay.
ya.
Thank you, Mr. Ivan.
Okay.
I'm very interested as have you explanation the microscopy, especially in magnetic force microscopy. Before 10 years ago, I have used that my spectroscopy using pulse laser, high nitrogen laser. I
Ablation,
use
okay.
that to characterize the half-life in the molecule. But after I hear your explanation about these tools that are very, very sophisticated, I think. So may you explain us how that contact mode as POJ proof, and have you mentioned that the current only 13 picoampere? How can looks like that, and why? How we are to analyze that spectrum? Is you use this instrument transformation, Fourier transformation and filter to get that spectrum? I hope you explain it. Thank you.
Yeah, thank you very much for your question. So, as I understood, the first one, I didn't get clearly what do you mean spectrum? But for example, for the contact measurements and the current measurements, so we just use a conductive coated silicon probe coated by like platinum, titanium, or gold. Then we approach it to the surface and apply some small voltage, like a few millivolts between tip and sample. And the sample, for example, is grounded. And so at some particular area where the Faraday current start to flow between tip and sample. And then in the measuring head, we have the lock-in amplifier, and it can be like, not lock-in amplifier, yeah, but to amplifier to measure the current. And then we measure, and it's very sensitive. So we cover to get such value of few femtoamperes, which is very small, which is very like comparable to the noise level. We need to cover the whole unit by protective cover, grounded, to make like a big Faraday shell to avoid some external noise appearing. And then we measure this current, conductivity current between tip and sample, even at this 30 femtoamperes. The typical range of the current measurements is from like a 10 femtoamperes up to 50 nanoamperes. So you can see it's still in the very nano or femto level measurements. So we don't need to measure some microamperes or milliamperes, because we want to apply very small voltage and measure at the very, very small level scale the currents.
Okay, maybe another one, sir.
Yeah.
How about the point-to-point resolution that's use the piezo proof? The resolution one point to another, and how can we understand the characterize of that material? Like as you before you have mentioned about the sample of medicine, how can we characterize the distance of the atoms?
Yes. The idea here that we have the scanner. We have the scanner which move the sample, or it moves the tip with regard to the sample in X, Y, and Z. So that direction is usually used for topography measurements. But when we do mapping, the scanner move our sample left and right. So we do like one line, then return, switch to next line in Y, one step in Y, then next one. And we can set, for example, the typical scan range is 100 microns, but we can scan also 5 nanometer only. And independently, we can choose different number of points. It can be from 16 by 16 points in XY map, or it can be from up to 8,000 points. So you can get, for example, 1 micron size with 8,000 points. In that case, the step size between 2 points in XY will be very small, will be like 1 nanometer or a few nanometers. And then this scanner is controlled by the electronics, and electronics applies this DC voltage, this DAC converter applies some volts to move the scanner in X and Y. So, and it slowly moves from left to right, then 1 step in Y, then again 1 step in Y, left, right, and then we get such a morphology relief for each line. Then we collect it to the matrix, and finally we have the 3D matrix of the morphology, or the same we do for any other properties, because we measure them in the same time with the topography. So when we stay in 1 point, we can measure the topography, we can measure magnetic properties, elastic properties, friction properties. Then the controller move the scanner with the sample to the next point. The step size can be 1 nanometer, 10 nanometer, or 100 nanometer. You can choose it by yourself in the software. And then finally, you get few signals from the single point, depends on what you need to measure. And then you have like few images, few maps of the different properties that you can compare, decide if they correlate each other, or maybe after you can zoom in some particular area and go for higher resolution if you are interested in some local area.
Okay, thank you, Mr. Ivan, and I to Rikson Siburian.
Thank you.
Thank you very much.
Dr. Krista Tarigan. Any question, our honorable participants? Do you have some question to Dr. Ivan? Well, just wait from the participants' question, Dr. Ivan. How about the maintenance this atomic force microscope?
So the maintenance for the atomic microscope, actually, the first thing that it requires always some accessories. I mean the cantilevers, the probes. So, and you need to decide for yourself which type of the probes and what is your how much probes you spend like per month or per year, and you need to program such a some budget just to get the new probes. In principle, if you operate accurately with the correct values, with the correct forces between sip and sample, then you can use one probe for several measurements. Okay. But sometimes it happens that you apply some force, but the sample can be too rough, for example, or it can be, there can be some particles, and during measurements you scan and you don't completely destroy your probe, but maybe it becomes not so sharp after a few measurements. Then you need to understand that if you want to measure some rough samples, it's still good. But if you want to measure some very fine, very small features on the sample, always is better to take the new probes with a guaranteed curvative radius, because in that case, you will be sure that this is like the top result, that maximum resolution you can get. For the other things, like for example, the software and is like a fully supported, free of charge for the lifetime of the instrument. So like every month we have some release of the new software for AFM control, for analysis software. So we add some new functionality, new filters, new components to the main software. So you can easily download it, reinstall, upgrade your software, and continue to operate without problem. And for the maintenance of some other mechanical or electronic components, actually it depends. For example, many of our instruments works from 2000 years up to now without any problem. So it's very old models that we don't produce anymore now, but they still work. But for example, in some regions, maybe with a high humidity or with a different climate which is changing, it's better to have some constant, more or less constant conditions in the lab. I mean, to put some air conditioning, to have the temperature between maybe 20, 25, and avoid very high humidity, because if you have a very high humidity, there can be some layer of the water not only on the table but also on some components on the scanner or maybe the controller inside, and then can cause some problem, or maybe it can damage some components. But for normal cases, if you have more or less standard recommended conditions, then no problem at all. And for the support, for the technical support of our company, so always you have the local representative support, you have our Ask Online service that you can go to our website and contact our engineer with your problem, and they will connect to you by TeamViewer, UltraViewer, and will help you to solve all the common issues. If you have some problem with the software or with the hardware, or if you just need to have some advice how to approach to some particular application, then we can connect remotely and give you some advice and show you which parameter is better to change or which parameter are not optimum and so on. So then Skype and so on. And if necessary, we have some temporary stock in our offices in China, US, in Europe. If you need some quick replacement just to not interrupt your study, we can do some first replacement, a quick replacement for the time of reparation of some problematic part as well.
Oke, thank you. Bapak Ibu mungkin punya pertanyaan, ada representasi dari Lab Sistematik Indonesia, ya, ada Bapak Direkturnya Pak Ponidi dan Pak Imran. Kalau Bapak Ibu punya pertanyaan, silakan in Indonesia ya, dengan Pak Ponidi dan Pak Imran. Silakan Bapak Ibu, mungkin ada pertanyaan ke representasi di Indonesia ya, Lab Sistematik Indonesia. Silakan. Soalnya kalau mau beli AFM-nya gimana gitu ya. Nah, bisa ke Pak Ponidi, di sini ada dirutnya. Oke.
Kalian harganya berapa kira-kira Indonesia
Ya,
Pak ya?
iya gitu. Nah, ya Pak Imran sama Pak Ponidi boleh ini, mampu nggak kita kampus kita beli gitu? Kira-kira harganya berapa ini?
Terima kasih Pak Krista. Jadi di NTMDT ini ada beberapa model. Jadi yang ada di Indonesia itu yang Solver Nano, yang sekarang ada di laboratorium nanoteknologi tempatnya Prof. Nurul. Kemarin sempat dipakai di Universitas Indonesia. Jadi ranknya kurang lebih di kisaran dari 1,5-an lah, yang paling murah itu. Dan perihal spare part tadi seperti dibilang sama Mr. Ivan, cantilever ya yang perlu diganti, dan hingga saat ini tidak pernah ada problem yang menyangkut tentang peralatan ini, dan engineer kita Pak Lisko Wari Antoni berserta tim sudah terbiasa menggunakan alat-alat yang berhubungan dengan mikroskopi termasuk SEM ya. Jadi sampai saat ini tidak ada hal yang begitu rumit dan bisa dikontrol dengan jarak jauh ya, pakai tim viewer oleh engineer-engineer kita. Jika memang menghadapi problem yang begitu rumit ya mungkin nanti pabrik bisa memandu peralatan ini gitu. Dan beberapa peralatan yang mungkin belum ada di Indonesia seperti kemarin kita install single kristal di ITB, meskipun kita belum mendapatkan training tetapi dengan teknologi tim viewer dan beberapa aplikasi lain itu sangat membantu sekarang ini. Jadi tidak ada istilahnya alat yang di universitas atau berbagai tempat lain itu yang tidak jalan. Saya pernah ke USU, banyak alat-alat yang tidak jalan, sangat disayangkan sebenarnya. Jika memang masih ada agentnya, mungkin bisa dibantu oleh mereka untuk bisa memandunya, Pak.
Ya, oke. Nah itu dengan 1,5 M itu performansinya sama dengan yang sudah dipresentasikan Pak Ivan ya?
Ada beberapa model tadi ya. Tapi nanti secara rinci ya. Mungkin lihat nanti aplikasinya seperti apa, kan tadi kita melihat aplikasinya cukup luas ya. Ada
Ya.
bidang material science dan biologi, termasuk juga dari virus gitu. Nanti tinggal ini aja coba, kan kita tidak semua memang itu kita tawarkan. Mungkin untuk beberapa lembaga riset yang aplikasinya begitu mendalam, ada tadi yang integra itu yang lebih komplit. Nanti saya coba ini kan update harga terakhir. Nanti akan dibantu oleh Ibu Sera yang support AFM yang selama ini komunikasi dengan Mr. Ivan Bikop, dan Pak Imran ya sebagai Direktur Operasional di Lab Sistematika nanti akan membantu memberikan support perihal komunikasi ya. Komunikasi karena memang peralatan AFM ini sebenarnya tidak begitu banyak di Indonesia, dan saya kira sangat penting di bidang untuk nanoteknologi untuk microanalisis ya, di samping mungkin SEM, kemudian TEM, kemudian XRD dan particle size. Jadi saya kira AFM cukuplah. USU harus memulai untuk wilayah Sumatera.
Oke, terima kasih. Mudah-mudahan decision maker-nya ya, boleh mengambil keputusan itu ya. Dan kita punya alat itu di Universitas Sumatera Utara ya. Memang kita nggak punya alat banyak, tapi punya satu yang luar biasa misalnya. Nah itu ya, mudah-mudahan. Oke, Bapak Ibu, masih ada pertanyaan? Do you have some question to Mr. Ponidi, Mr. Imran, and also Mr. Dr. Ivan?
Thank you, Mr. Ivan.
Thank you,
Halo
Mr.
Ivan,
Fahri.
ya.
Thank you.
Yeah, you support my company about AFM, ya. Mr. Imran, Miss Sarah, Miss Dewi, Lisko, Aris Faisal in my company. If you okay, we can make a webinar every 2 months in Indonesia.
Sure.
I think so many institutions. I think it's very interesting about the AFM. Yeah.
Yes, very good. We can also make some dedicated webinars for some particular application. I can invite my colleagues from application. They can make some more deep explanation of some particular area or
Okay, well, yeah, very nice webinar today. If you don't have again the question from the attendants, I think we have to close this webinar.
Great. If any question appear after, you can address them by mail.
Dr. Ivan, there is a hands up. Ibu Agustriana, silakan. Ibu Agustriana, ada pertanyaan? Silakan Bu. Ya.
Okay.
Ya, thank you.
Hello, Mr. Ivan.
Hello.
Just call me Anna from National Research and Innovation Institution in Indonesia. I want to ask you about what to say. In your tools, you use what is the difference between what's the name of the instrument you said before, please? IT, what? I never hear about that. Before I use FSM and SEM and TEM. And what is the difference that instrument, and is it better than the instrument that I used before, FSM, TEM, or that, etc. Just it.
Sorry, which instruments did you use before? Was it AFM or as the analytical instrument?
It's analytical instrument.
She used the STM and
STM and
PEM and
STM.
Yeah. So the main difference is that for AFM, you don't need to have the conductive surface only, because AFM use the optical registration system instead of the tunnel current. So it means that you can apply the AFM to any surface you want. It can be conductive, not conductive, biologic, soft, hard. It can be powder in air, in liquid. You can measure in the gas, environmental, or some aggressive media as well. And the other things that you can, apart from the topography, you can get not only electrical properties like in STM, but also magnetic, mechanical, friction, piezoelectric properties. And plus, you can easily combine it with the other analytical methods. So this, I think, is main advantages, just a big one in comparison with those techniques you mentioned.
Okay, thank you ya. Thank you.
Okay.
Okay.
Sorry.
Triana.
Another question. Can we use that instrument in a live sample?
In the live sample?
Yes.
Yes, you mean kind of biologic sample which stay in the solution?
Oh, or is it the material only, or a metal, something like that?
I don't understand clearly. What do you mean live sample? You mean
because I use FSM just to analyze the material like metal, carbon, or something like that.
yeah?
But this one, can we analyze a bacteria?
Yes, exactly. I show few images of the liquid for biologic objects that you can measure in liquid, in air, or any kind of special solution, aggressive solution. So you can measure the viruses, you can measure bacteria. Just recently, this year, our users did some measurements of this COVID viruses, also just to analyze their structure and their properties in the liquid. Yeah.
Okay, thank you, Joseph.
Okay, thank you, Ibu Agustriana. Yeah. Well, all of participants, time is behindering to all of us. Yeah, because limitation of time, and we have already around more than 2 hours. Yeah. Close 2 hours. Yeah. So on behalf of Karbon Research Center of University of Sumatera Utara, and also our Vice Rector and our Dean and our head of Karbon Research Center of University of Sumatera Utara, and also all of the participants, we would like to deliver our thankful thank to Dr. Ivan, who would like to deliver the nice presentation today, and we may catch many things, the fruitful things based on our atomic force microscope. Hopefully, we may keep contact and also keep spirit to share many experience and many knowledge, yeah, to all of us, and we may emphasize each other. Next, we would like to thank to Bapak Ponidi, ya, Direktur PT Lab Systematic Indonesia, and also Bapak Imran, ya, kolega saya yang mengorganize acara kita pada hari ini. Kami berharap kita masih bisa melanjutkan terus ya dengan topik-topik yang lain ya, khususnya dalam instrumentasi yang sangat kami butuhkan di tingkat universitas, baik di Universitas Sumatera Utara maupun di luar Universitas Sumatera Utara. Bapak Ibu yang kami hormati, ya, hari ini bergabung begitu banyak kolega-kolega, sahabat-sahabat, teman-teman yang konsen di bidang material science atau bidang fisika, kimia, biologi dari Universitas Sari Mutiara, dari Universitas Mula Warman, dari berbagai institusi lainnya. Kami mengucapkan terima kasih yang sebesar-besarnya buat Bapak Ibu for your precious time and join and gathering with this webinar. Kami berharap kita bisa bertemu lagi di acara-acara yang akan kami gagas. Kami mengharapkan Bapak Ibu tetap mau bergabung dan berkontribusi di acara Pusat Unggulan Iptek Karbon Universitas Sumatera Utara. Akhirnya, Ibu Ketua, ada yang mau disampaikan lagi, Bu Ketua?
Tidak ada Pak Rikson, cuma terima kasih barangkali
Ya,
pada
silakan.
Pak Ponidi dan Ipan Biakov. Thank you very much. Nah, itu aja Pak Rikson.
Baik, oke. Akhirnya kami ucapkan terima kasih kepada semua komite, ya, panitia yang sudah mempersiapkan. Dan informasi tambahan Bapak Ibu mohon diisi absennya untuk keperluan mengirimkan sertifikat kepada email Bapak Ibu, ya, atau WhatsApp yang sudah diisi. Kami akan menyiapkan sertifikat secepat mungkin sebagai penghargaan kami, reward kami kepada kehadiran Bapak Ibu di acara kami ini. Akhirnya ke kebun binatang melihat macan, belang bulunya, besar taringnya. Capek dan lelah memang langganan. Di akhir masa pasti bahagia. Semoga kita bahagia di setiap aktivitas kita dan tugas dan tanggung jawab kita masing-masing. Atas nama Pusat Unggulan Iptek Karbon kami ucapkan terima kasih. Thank you Dr. Ivan dan see you
Thank you very
again
much.
in
Thank
the
you very
other
much.
session.
Okay,
Thank
thank
you
you,
very much.
Dr. Ivan.
Terima kasih Bapak Ibu.
Thank you. Bye-bye.
Terima kasih, bye-bye Dr. Ivan.
Bye-bye.
Thank you Pak Imran, Bang Koniti, dan teman-teman sekalian.
Wow.
Thank you.
Oke.
Ponidi, sebentar Ponidi.
Yang 1 juta.
Ya,
Ponidi,
Bang Ponidi, hidupin mikrofonnya. Pak Krista masih mau bicara nih. Kangen lagi. Ya, Bapak Ibu yang mau live silakan. Ini Pak Krista sama Pak Ponidi ini mau temu alumni kali.
Pak Ponidi, mana tadi Pak Ponidinya?
Udah itu masih ada. Masih ada.
Oke.
Ya, halo Pak Krista.
Nomor teleponnya nomor berapa Pak?
Ada tadi 0821
0821
1191.
Saya Bapak kirim tadi Pak Ponidi.
Ibu Mar pengatakan 2590.
2590.
Iya.
Terima kasih Bu, maaf
Oke.
ya sudah gabung dengan kita. Terima kasih Bu.
Thank you.
Pak Rikson, kan kalau tidak salah kan besok saya ada telekonferensi dengan perusahaan Kameka Amerika perihal ini atom probe tomografi, dinamik elektron sendiri sama elektron probe mikroskop untuk penentuan tanggal ini webinar yang akan diadakan.
Ya, nanti kasih kabar sama kita, mana tahu kita tertarik khususnya
Ya,
di instrumen lah.
Kalau ada emailnya nanti biar di invite sama Pak Imran.
Boleh. Saya
Tanggalnya kalau tidak salah tanggal 12 Oktober.
boleh Pak. Saya kirim.
Nah, jadi nanti bersama ini teman-teman yang lain mungkin ada dari ITB, dari BRIN kan sekarang lembaganya kan LIPI Batan, kemudian BPPT kan sudah dari BRIN. Jadi alat ini kan memang belum ada di Indonesia kan. Ini alat untuk atom probe tomografi ini kan termasuk salah satu alat yang bisa dipergunakan untuk material karakteristik tuh. Ya mudah-mudahan ilmu ini bisa bermanfaat lah buat kita untuk kita pelajari lah minimal ya. Kalaupun bangsa kita belum punya alat ini, saya kira ya mengenal kulit-kulitnya dulu. Mungkin ada beberapa teman yang sudah pakai di Prancis, kemudian ada yang pakai di Jepang itu. Nanti ada pembicara dari Jepang itu juga. Saya juga belum pasti, mungkin besok pembicaraan saya pagi jam 10. Jadwal pastinya nanti saya info lah. Terima kasih banyak Pak Rikson.
Terima kasih.
Ya, Bu Mar Pengatun,
ya.
Bu Nur Sahara, ya, Bu Popi tadi kan, ya terima kasih juga Bu
Ponidi.
Iya, kapan-kapan lah. Udah lama nih nggak boleh pulang ke kampung nih, udah 3 tahun nih nggak boleh pulang karena kopi. Semoga sehat selalu semuanya ya.
Amin. Oke, kita live ya. Sampai ketemu lagi teman-teman, Bapak Ibu.
Iya.
Dadah.